Bradford. This meeting is being recorded. Welcome to today's webinar. My name is Kathy Hoverman, and I will be moderating this session. The webinar series is brought to you all by the ASCE Environmental and Water Resources Institute and AFS Bioengineering Section's Joint Committee on Fisheries Engineering and Science. The series began in 2015 to share information on fish passage, dam removal, and related topics. Since the inception, we have provided free quarterly webinars every year, and today is being the third webinar of 2020. For some additional information on our committee, as well as links to past webinars, the link I dropped in is supposed to take you to the website. Looks like that's not working, so I will drop another one in a little bit later in the talk. Just for your information, we will have one more webinar this year, and that will be on the ecological responses to dam removals on the Elwha River in Washington State. That is different than what our website says. We had to shift a few things around due to some conflicts, but it will be on the Elwha. All right, so let's talk about today's speakers. We've got a duo presentation here. Presenters Heather Hanson and Jess Straub. They are both fish passage engineers from the U.S. Fish and Wildlife Service in Alaska. And yes, that means they got up early to put their faces in front of you. So we appreciate the early morning for them. Heather works on habitat restoration projects around the state of Alaska, replacing undersized culverts and helping to restore habitat connectivity for Alaska's salmon. She started her career working, oh, sorry, my cheat sheet got pushed around. Hang on, we're good. She started her career working on fish passage structures on the Columbia River dams in Washington State in 1993, and she grew up in Walla Walla, Washington. Has a BS in civil engineering from the University of Idaho. And Jess is an engineer in training working in data acquisition, 3D design and modeling, and project oversight. She holds a BS in environmental engineering from SUNY College of Environmental Science and Forestry and Syracuse University. And just for everyone watching, they have told me that they might have some QR codes so that you can scan those and see some cool videos at some point in their presentation. So if you've got your phone ready and that scanner available so that you can click that when the opportunity comes up. And with that, I'm going to turn it over to Heather to kick off this presentation.
Thanks, Kathy. Sorry about
no worries.
It's always something. So thanks for inviting us to present today to share some of the work we have been doing in Alaska to restore ecological function at stream crossings. Before we start, I want to acknowledge the stewardship of the Dena'ina people on whose homelands we live and work. I also want to acknowledge the support of our partners, consulting firms, and contractors who worked with us to develop, design, and construct the projects we are going to show you today. We have attempted to acknowledge folks throughout this presentation, and I apologize in advance if we inadvertently missed anyone. So a bit of an outline of what we're going to talk about today. We're first going to give you an overview of ecological functions of streams. And then we're going to talk about some techniques that we use to maintain those stream functions. First looking at crossing structures and then moving on to channel bed features. And then Jess is going to talk a bit about bioengineered banks, and then we'll move, I'll give you a wrap up with some economic issues there. So stream ecosystem functions. Streams provide many ecosystem services to aquatic and riparian communities. These communities are more than just a collection of organisms. They are interconnected by numerous ecological relationships that are both biological and physical. Streams help support those interconnected relationships. This is a list of some of the functions that are important to stream health and ecosystem health. All of these processes can be disrupted by man-made infrastructure such as undersized culverts. In the next few slides, I will give you an overview of these stream functions and some of the negative impacts that we are concerned about in our habitat restoration work. In order to understand stream ecosystem function, it's important to broaden our vision and think about the wide variety of aquatic and terrestrial species that are reliant on healthy stream corridors. Some of these species are strong swimmers and excellent jumpers, like adult salmon, but others can't jump at all, like Pacific lamprey. And some terrestrial species may need extra headroom, like this moose. Our restoration work focuses on removing or replacing undersized culverts on salmon streams. So I want to elaborate a bit more on the habitat needs for salmon. Rearing habitat for juvenile salmon is often the limiting factor in the success of a stock or population. In Alaska, coho, chinook, and sockeye salmon spent their first 1 to 3 years in fresh water. Salmon use streams to move between freshwater habitats in their early life stages. Salmon move up and downstream to find optimum water temperatures for feeding and overwintering. Lake temperatures can be too hot in the summer, so they may move to small headwater streams. In the winter, small streams often freeze solid, and the fish will move to lakes or larger streams. They also move to find food, eggs, decaying salmon, caddisflies, and other insects. Very small streams can help juvenile salmon escape from larger predator fish like trout or pike. Small to medium-sized streams are where we often find undersized culverts and opportunities for our restoration work. We focus on the needs of juvenile salmon and their habitat because their survival is important to increasing the overall abundance of adult salmon. So streams are more than just travel corridors for aquatic and terrestrial species, though. They also convey wood debris and other organic materials. Woody debris is a dominant habitat-forming feature in forested streams. Debris accumulations create pools, scour holes, and change patterns of sediment deposition within the active channel. Wood also provides cover and a home for prey species and reduces water velocities. Habitat restoration projects often add wood to a stream because it improves spawning and rearing habitat. Undersized culverts that interfere with the transport of woody debris can negatively impact habitat diversity and maintenance. Undersized culverts also impact sediment movement. Basically, you can think of culverts as small dams that trap sediment on the upstream side, as is shown in this picture. This happens when the water backs up at higher flood flows. Unimpeded sediment transport is important for many reasons. It creates complex channels, bars, riffles, and pools. It protects eggs and juveniles from high flows. It provides habitat for invertebrate prey. It sequesters and recycles nutrients. And it provides a vastly increased surface area for biofilm and algae. Groundwater connectivity is another important issue for maintaining stream function. The hyporheic zone is the region of porous sediments where groundwater and surface waters exchange, and it is important to stream health. It helps sustain microscopic creatures and other invertebrate prey species, and it also improves water quality. Connectivity through this zone helps to maintain cooler temperatures in streams and wetlands during hot, dry periods, which is important for salmon to survive and thrive. We often prioritize restoration projects in streams that have a higher level of groundwater connectivity because they are important thermal refugia for juvenile salmon when temperatures rise in the summer. Nutrient cycling is another important stream function. Salmon is a keystone species, and aquatic connectivity is necessary to make sure adult salmon can return to spawn, but also to provide key nutrients to the ecosystem. One study in the Pacific Northwest documented 137 species as dependent on salmon. 41 are mammals, including orcas, bears, and river otters. 89 are birds, including bald eagles, Caspian terns, and grebes. 5 are reptiles, and 2 are amphibians. In that study, they found that just 6 to 7% of historic levels of marine-derived nutrients are reaching streams. Some streams that are thought to have habitat deficiencies are in some cases just starved. In Alaska, salmon-derived nutrients can persist in stream biota up to 9 months after inputs. So most people picture a stream as a ribbon of flowing water. but the main channel is a small part of a stream corridor. This slide shows the wide variety of important habitats that are available to many different species in the floodplain and riparian areas in stream corridors. Floodplain habitats are especially important for juvenile salmon. They provide cover from predation, refugia during high water, and food during their first few years of life before they smolt out to the ocean. I think this visual is useful to compare a stream that is providing minimal ecological function versus one that provides for a full suite of stream functions. I'm picking on this creek on the left because it is from my hometown. This concrete line channel was constructed in the 1930s after a major flood event. Well, fish passage has recently been improved at this location, roughness elements here, and resting pools have been added. Most of the other stream functions have been lost due to the concrete lining and the levees that continue for several miles and cut off all floodplain, groundwater, and riparian area connectivity. Conversely, the stream on the right has deep pools, cool water, good spawning gravels, woody debris, and low banks that allow for connectivity with the floodplain. It's pretty much salmon heaven if we make sure that they can cross the road and access this habitat. This slide depicts several different approaches that we could take to construct a stream crossing for a road or trail. Depending on how the crossing is constructed, it will provide for different functions and a range of ecological connectivity. At the bottom in detail E, you will see a traditional culvert that is just designed to pass a flood flow. At the top in detail A, we see a bridge that spans the floodplain and has little to no negative impacts on aquatic and riparian connectivity or other stream functions. It would be great if we could afford to put a full valley spanning bridge at every crossing, but many times we can't. In order to be able to cost effectively construct most crossings, we usually end up using the approach shown in details B and C. This requires a crossing structure that is at least bankfull width or greater. Floodplain culverts may also be added to provide some floodplain connectivity. And here's an example of a culvert that is bankfull width with a floodplain culvert that is set at the bankfull elevation. Our functional goals for new culverts and bridges that we replace are, we are looking for a dynamically stable geometry. We want to maintain sediment transport and equilibrium at the crossing with the upstream and downstream reaches. We want to see natural substrate in the pipe. We want to make sure to provide for space for woody debris to move through the system or move through the culvert at high flood flows. We want to provide passage for all aquatic organisms. We want to provide terrestrial wildlife passage as much as possible. Obviously, that's somewhat limited in some cases where you don't have the headroom for the larger creatures to go through, but there are some. Just providing banks and overflow culverts can provide that. And we want to increase floodplain connectivity as much as possible. Finally, we do design for a 100-year flood. Typically, the design flood on roads in Alaska is the 25 to 50-year flood. By designing for the 100-year flood, we hope to improve the longevity of these crossings we invest in and improve the ability of these structures to withstand the higher flood flows that we are seeing in Alaska due to climate change. In order to achieve our stream function goals, our approach has been to heavily rely on a geomorphic analog for design of a stream crossing. We try to mimic the reference reach hydraulic geometry up to the bankfull stage, which is the flow stage where water leaves the channel and spills onto the floodplain. We rely on the bankfull geometry rather than the active channel width or the ordinary high water width because the bankfull geometry is a result of the hydrologic and physiographic setting of any given stream. In most systems, the bankfull stage falls between the 1 to 2 year flood flow. If possible, we collect a reference reach profile and cross-section from the same stream where the crossing is located. And I say if possible there because sometimes there just isn't an appropriate reference reach for that, but Yeah, if possible, we try to stay on the same stream. The data we collect includes the bankful channel slope, width, mean depth, max depth and area, and the low flow channel area and depth. Mimicking the reference reach geometry helps us to maintain sediment transport and equilibrium with the natural channel. To understand why this works, I want to review the basic equation for shear stress, which is the force that is exerted on the channel bed to mobilize sediment. In this equation, tau is the shear stress, gamma is the unit weight of water, sine alpha represents the channel slope. So for a given slope at steady flow, the shear stress is dependent only on the depth of water. The deeper the water, the higher the shear stress, which is what you see in this graph here. This equation has implications for how we design the channel at our crossing. In order to maintain sediment transport equilibrium between the natural channel and the one we construct at our crossing, we maintain the hydraulic geometry at every stage up to bankful. This is because the flows up to the bankful stage are responsible for removing the majority of sediment in an alluvial system. In the past, when constructing a new channel, engineers have often increased the width to add a factor of safety. However, that results in lower depth and lower shear stress. So looking at these two cross sections, channel A is a bit wider and shallower than channel B at the bankful flow. This means channel A is going to be less competent to move sediment than channel B. In order to avoid aggradation and resulting loss of the low flow channel, we try to maintain the mean flow depth for all discharges up to the bankful stage. So that covers flows up to the bankful stage or up to the 1 to 2 year flood flow. But at higher flows, unless our crossing structure spans the full floodplain width, we're usually going to be somewhat constricting the flow compared to the reference reach. This creates higher shear stress in the crossing structure at those higher flood flows. So here we're talking about the 2 to 100 year flood flows or greater. We have some strategies for dealing with that. This is one approach that I have already shown, where we provide a bankful with primary culvert and floodplain culverts with their inverts set around the bankful elevation. In the primary culvert, we provide headroom for woody debris to ensure that debris can move through the system and help maintain habitat complexity. The floodplain culverts help to provide floodplain connectivity and reduce the shear stress in the primary culvert. And this is an example of a small bankful width culvert with floodplain culverts that was constructed in Tyonek, Alaska. Here's another approach that is a wider culvert with stream banks constructed inside. Because maintenance of these banks is important to maintaining the bankful geometry, we design these to be stable up to a 100-year flood. Constructing stream banks inside a culvert improves stream function. Pit tag studies have shown juvenile salmon passage actually increased once the flood flow overtopped the banks because the fish were able to use the slow water and roughness in the banks. So this is pretty cool how it really emulates what would happen in the natural stream, where juveniles would use the floodplain habitat to escape high velocities. And this is an example of a culvert that was constructed with stream banks inside. The substrate in this culvert was designed to be stable to the 100-year flood flow. It has medium and finer particles mixed into it to make it a well-graded mixture, and Jess will touch more on that. This picture was taken about 2 years post-construction. Open bottom culverts are another option for improving stream function at a crossing. They allow for hyporheic exchange to take place and improve groundwater connectivity. We often end up using these structures on medium-sized and larger streams. This is an example of an open bottom culvert. Large rocks were used for the banks inside this culvert, which is fine, but they could have been better filled in with sediment, prevent fish entrapment on the falling limb of the hydrograph. Overall, this culvert has been functioning well for the last 8 years. I want to point out that sediment transport is happening through the channel cross-section, with spawning-sized gravels being transported along the stream bed. Tidally influenced crossings are challenging. This site originally had a fish ladder that was ineffective most of the time. You might think that culverts located where stream outlets into the ocean only needs to be passable to adult salmon. However, there have been telemetry studies that documented juvenile salmon moving through saltwater between watersheds during their rearing life stage. So we try to make tidal culverts passable to all life stages 90% of the time. At this project, the culvert was replaced with a bridge and a roughened channel was constructed from the crossing down to the mean low tide elevation. Despite the large waves that sometimes hit this beach, the channel is still looking good 4 years after construction. Now we are going to dive into how channel bed features can be used to improve stream function. This is a list of the bed features that we are going to show you. We're going to show you some that have been successful and some of the pitfalls and problems we have run into as well. One of our major concerns is the low flow channel. During low flow times of year, we want to make sure that the flow is concentrated into a low flow channel that will provide sufficient depth for aquatic organisms to continue to move through the system. We use our reference reach cross section to size the low flow channel. We have found that inside a culvert, forcing features constructed of larger, stable rock are needed to maintain a low flow channel. So we designed these forcing features to the 100-year flood. We think of these features as emulating the wood in a forested stream. They create local scour, which helps to maintain the low flow channel. The picture on the left shows a rock band and the picture on the right shows a rock cluster. The rock bands might be used if the culvert is not wide enough to construct rock clusters. The rock clusters produce scour by changing the flow direction at low flows. These examples are both bankful width culverts, so there are no banks constructed inside these culverts, and we are only looking at forcing features that influence the low flow channel. This culvert was designed with substrate to be stable up to the 100-year flood. It is located at a lake outlet where stability was important because there are several businesses upstream and docks. Another issue with a lake outlet is there's virtually no sediment supply that's going to run through this culvert from the lake. So we designed all of this for the 100-year flood, but during construction, we actually added some larger rocks as forcing features to really force that low flow channel. A couple of lessons learned on this culvert. I wish we would have added some finer materials in the top 6 inches, kind of in this area, to allow for some scour processes to happen. Also, we should have sloped the bed away from the culvert walls. Fish can be trapped here at low flows. This is another example of rock clusters in a bankful width culvert. The addition of finer substrate in the low flow channel helps to allow the scour to happen and better maintain the low flow channel. In the future, I would like to try adding some finer substrate below the low flow channel as well to allow for channel adjustment. And with doing that, we still need to maintain our stable straight substrate in the culvert so that it doesn't get washed out at those higher flood flows. So moving on, here's an example of a riffle that was constructed through a culvert. Larger rocks were used to create banks inside. This culvert went through a 100-year flood event in 2012. The banks remained intact and the bankful geometry has also been maintained. Overall, a constructed riffle is a great way to go, as the riffles in nature tend to be located on the straight sections of streams. You can see in this photo that finer gravels are moving through this culvert as they would in the natural channel upstream and downstream of the crossing location. Riffles provide good habitat without needing a lot of special rocks because there's generally lots of variation in the bed. We often see adult salmon spawning in culverts like this. This culvert used rock bands for the low flow channel forcing features. So this, excuse me, this photo was taken 8 years after a 100-year flood event. This is the only riffle pool sequence we ever attempted inside a culvert. Riffle pool sequences on natural streams are a result of stream meanders. The rotational forces on meander bends maintain the pool geometry on these types of bed features. Inside this straight culvert, we did not have the meandering plan form to maintain the pools over time. They also took a lot of time and oversight to construct. After a 100-year flood, the substrate in this culvert flattened out, and it has turned into a roughened riffle. There isn't really a low flow channel because we don't have any forcing features. This is not an approach we would take again. So habitat rocks are great for providing resting places for fish, but they need to be used with caution. Some rules of thumb that we have for habitat rocks are, we basically don't want them to block too much of the bankful channel or the low flow channel. They need to be placed so they don't cause excessive erosion. And we prefer to keep them about 1 to 2 diameters away from the banks. We also size these for a 100-year flood and place footer rocks below them to prevent excessive scour. And on this culvert, I think the lesson learned here was we kind of had some habitat rocks that were placed at the upstream end, and actually the way they were clustered here, they forced the flow into the culvert wall. So yeah, just definitely following these rules is a great idea. So I will turn this over to Jess, and she will now share a project that we completed recently using step rules for the channel construction.
Great, thanks, Heather. So this project was located at the outlet of a small lake in the Matsu Borough. The road prism here is acting as a dam and creates the lake. And one of the goals of this project was to maintain that lake elevation, as there are floatplain docks on the lake. So the existing culvert had a steep outfall that was not passable to juveniles or adult salmon. So the design concept was to relocate that outfall and tied into one of the newly constructed, or one of the existing relic channels, effectively bypassing the existing culvert's steep outfall channel. And so here's the profile view and a detail of the grade control structures from the design drawings. The channel was designed at a 3% slope with 6 inches of elevation difference between each grade control feature. The grade controls were shaped to match the reference reach cross sections and were well embedded into the substrate. We didn't ask the contractor to attempt to form full pools here, but rather we left that formation to be done by the stream. Here are some photos of these being constructed. So larger rocks were used to construct the grade control features. The total length of stream that was constructed here was 230 linear feet, and we had about 13 of these grade control features installed. The footer rocks here were embedded into the substrate and tied into the banks as designed to really ensure that excessive scour doesn't cause these features to fail. And this last photo is a week after construction. And this is that same channel 1 year after construction. We are really happy with the way that the grade controlled features have held up and established their scour pools. So the V-shaped structure has really successfully concentrated the flows and created a small, stable step pool. And earlier this week, I took measurements of the max pool depths to see how the grade controls were functioning and the pool shapes, how they had been developed. And the pool had scoured out an additional 0.45 feet since construction, which is completely fine. And the overall water surface drop from grade control feature to the next one maintained that 6 inches. And so this location this last year has experienced higher than average flows. So we're happy with how it's held up, and it's been a good test of really just the performance of these features in this constructed channel. So during construction of these stream bed features, we work really hard to avoid any kind of construction issues that could result in any degradation to the stream's functions. The installation of coarse stream bed material without any fines led to a loss of surface flow, which you can see in this project above. And the issue led to the channel going dry, and it can also lead to fish entrapment in the unfilled void spaces when that water level drops. So in order to avoid this problem, we use techniques to ensure the creation of a strong stream bed that really mimics the natural bed. Having well-graded substrate is one of these techniques. So it's a technique to ensure we use a well-graded substrate with a mixture of coarse and fine material. During construction, we mix the substrate materials prior to placement in the pipe. This is really the only effective way to get a well-mixed, well-graded substrate. Another approach that we've seen used is to place the larger material first and then attempt to wash the finer material into those void spaces. And a problem with this approach is it's really impossible to get that mid-sized material into the void spaces, and you end up with this gap-graded material, and the finer materials end up getting washed out in higher flood flows with this approach. So we don't recommend it. Here is an example of a well-graded substrate being placed. In this photo during construction, you can see the pre-mixed pile in the background prior to placing it into the pipe. And on the right is that finished product. So the substrate contains a well-graded mix of riprap and finer materials with a max rock size here of 30 inches. And this culvert was constructed at a lake outlet in Kodiak and is a fairly steep location. So those factors drove the designer to use a larger size of rock than we might typically see in a stream this small. And the contractor did an excellent job of placing these rocks inside the culvert to really mimic the bedrock controlled reference reach for the system. So filling in those voids, yeah, one vital technique to create a stable stream bed and channel forcing features that are really going to last is to wash down the substrate and fill in those voids. So we have this well-graded pre-mixed substrate of coarse, medium, and fine material, and we've constructed the channel's geometry or any stream bed features. And now we are ready to wash the substrate down for the entirety of that newly constructed channel. On this slide is a photo of a constructed channel pre-wash. This second photo can show you the post-wash and pre-wash and all those fines settling down into those voids. And this last photo is after that material has been washed down a few times and the voids have been filled. So this process really allows for that larger size material to remain on the top of the bed surface and create an armor layer on, which is really similar to natural stream processes. And the armor layer protects that finer material within the substrate, which really reduces the permeability, keeps water flowing on the surface. You can see water pooling here. And we really do have to do this sometimes, 2 or 3 times to get the desired outcome. We have a video that demonstrates some of the washing and the fine techniques on how to really create that well-graded, low permeability substrate. And you could scan the QR code here, but also all of our QR codes will be available after the presentation today. So moving out of the stream bed and onto the stream banks, we use bioengineered stream banks to tie the newly constructed stream section aesthetically and structurally into the stream channel upstream and downstream of the crossing. And so the root system and the foliage, they provide protection from prey species. They increase the roughness to really reduce those water velocities and provide shade to reduce water temperatures. We'll use bioengineered stream banks because they're sustainable, they're cost effective, and they really are a great way to stabilize the bank channel and help provide a continuous riparian corridor, which will improve habitat connectivity, not just for aquatic life, but terrestrial species as well. And we typically follow the Alaska Department of Fish and Game Stream Bank Revegetation and Protection Manual, which is available with this QR link. And ADF&G right now is in the process of updating this manual, so we expect to see a new updated version any day now. And I just want to note that to protect the culvert and the road features, we will use riprap and headwalls at the inlet and outlet. Towwood is, putting towwood in the banks is one of those bank reconstruction techniques that is not currently in the ADF&G manual, but we have found that it's very useful for stabilizing the toe of the slope. And it really allows for revegetation to establish on the bank benches upstream and downstream of the culvert. This is a great technique in lower energy systems that have good floodplain connectivity. So in this drawing detail above, with the corresponding construction photo, we can see the interlocking of those 4 to 8 inch diameter logs, which are used with rocks and then backfilled with topsoil to the bank full elevation. And now that the top of the bank is ready to receive vegetative mat, which is great. Sometimes we have to use smaller branches in lifts, maybe to just bring that bank up to the appropriate design elevation. In this example, that was not needed. Vegetative mat. So here's an example of vegetative mat being placed along a stream bank. We prefer to always place vegetative mat for the first 4 to 6 feet along the bank because it just establishes so much faster than seeding. And the vegetative mat is usually sourced near the construction site. And if possible, we harvest it and transplant it on the same day. We've had just really great success with the plant survival, and we are able to establish a more appropriate riparian species around the stream by using this method. So a lot of landowners and engineers have concerns about these techniques and the cost of these techniques compared to traditional culverts. So Heather is going to go into this a little more in detail.
Yeah, as Jess said, a common complaint is that it's too expensive to construct these larger crossings and replicate the natural stream inside the structure. However, we need to consider life cycle costs to understand why this makes economic sense in the long run. Undersized culverts result in debris plugging, road failures, and icing that often flows over the road, as you can see in these pictures. Maintenance costs and emergency replacement costs are high. One study in Wisconsin looked at 461 undersized culverts and considered only the cost benefits of reduced replacement and maintenance cost. Culverts sized at 1.1 times the bankful width resulted in fiscal lifetime net benefits to over half of the culverts sampled. Other cost benefits analysis have reached similar conclusions. Investment in ecological function can pay off even when you just consider the maintenance benefits. Besides maintenance and flooding costs, though, undersized culverts result in a loss of ecosystem function and fish habitat. In Alaska, this has consequences for the commercial seafood and tourism industries. These industries rely on functioning habitat to help maintain healthy fish populations, which are a renewable resource that form the foundation of these industries. Finally, by maintaining functioning habitat, we are helping to protect a sustainable, reusable resource that will continue to benefit future generations. So the projects we shared with you today would not have been possible without a long list of partners who care about reconnecting and restoring salmon habitat in Alaska. I want to give a big thanks to everyone who gave their time, energy, and funding to help make these projects possible. And I apologize if we missed anyone. This last slide is a compiled list of resources for some things we have covered today and more. So we've got our stream crossing workshop that we did in the spring, a video playlist there, and we've got some construction videos that Jess has put together that can be helpful for contractors, I think. And then we have culvert design guidelines that are available online for Alaska that really address these ecological function concerns. And then the Alaska Department of Fish and Game Stream Bank Vegetation Manual is also available online. So we really appreciate the chance to share our work and experience with restoring aquatic connectivity in Alaska today. And we want to thank everyone who took the time out of their busy schedules to attend. And we will go ahead and take questions. And
Wow. Yeah, you got
Okay.
a lot of questions here. People are all over this. I think some of these you may have answered once we really got going, but I'm still gonna start at the top and give you a chance to just say, yeah, that was covered, or maybe go over it really quickly. All right, so first one, how do you avoid or address sediment and debris buildup? And I believe that came in when you were showing your kind of the early culverts you were sizing, the early pictures of the culverts you were sizing.
Right. Well, we don't get debris buildup because we allow the debris to pass through the culvert. So that's how we avoid or address it.
Mhm. All right. Have you seen large woody debris moving through these culverts?
Yes, we have. In fact, we had a project where we put some woody debris out for habitat, and the next year it all washed through the culvert. So
Sounds like another great QR video to put together.
Another lesson learned.
All right. Have any significant erosion occurred on the banks within culverts? Have they required any repairs?
Yeah, I think we have lost some stream banks, really in the culverts. And when that happens, the problem is that we can have some, we can lose the low flow channel basically because it gets widened. And we had a culvert that was designed at 1.5 times the bankful flood or bankful width, and that ended up needing some repair. We've also had a culvert that basically head cut because we didn't get the grade right. We've had culverts that were undersized a bit because we just didn't get we didn't make them wide enough. So we started really sticking to this bankful width. And since we've started really sticking to the bankful width, we haven't seen that problem.
Okay. Looks like a clarifying question here. What is the difference between habitat rocks and forcing features?
Yeah, I think habitat rocks are really just placed for habitat, where so they could be sort of random rocks placed in the culvert within the limits that I gave. But forcing features are really meant to maintain that low flow channel. So they are larger rocks that are shaped to the channel shape and provide, really force scour to happen that helps maintain the low flow channel.
It's kind of a good timing on another question about habitat rocks. Are there any concern putting habitat rocks inside the culvert causing debris becoming impinged and potentially preventing conveyance within the culvert?
Yeah, I think that they could hang up debris a bit. So I think habitat rocks need to be used sparingly. They're not the end all be all for sure. And we often don't put them in at all. As I explained, like a rocky riffle really has plenty of roughness.
Mm-hmm.
So while what I find is everyone, wants to put them in, that we all built these little streams when we were kids, and we want to build dams and put in habitat rocks. So to know what the rules are if they're going to get put in.
Yeah, that sounds like a good topic conversation too, as far as like corresponding that with length of culvert or something to that effect. Okay, kind of moving on to a different topic away from the habitat rocks. What about corrosion issues, since it's CMPs? Person said, is there fill covering the CMP, and it's possibly concrete would protect or maintain culvert if CMP rots out?
CMP is corrugated metal.
Corrugated metal pipe. So most of the pictures you've shown have all been metal structures. So I think they're just thinking about corrosion issues and things like that.
Okay. So we tend to use aluminum because they're more corrosion resistant. That's not always possible, but other, and just looking at the 50-year design life and having appropriate galvanizing thickness if we are going to use galvanized. The other thing is banks in a culvert can really help protect against those corrosion issues because they keep the water away from the wall most of the time. So we do see less corrosion. And yeah, I think I have not seen a lot of corrosion issues in the pipes we've installed, but we've only been doing this for like 20 years. So, that's probably still going to play out there. Yeah.
Not quite enough history on that. Okay, great. For Cloudy Lake Outlet, can you explain the use of the willow fascines? It seems like they did not survive based on the photos.
I'll let Jess answer that.
Yeah, so we recommend planting dormant willows, and in this case, the willows that were installed were not fully dormant, and so they were using a lot of energy and growth in the wrong direction, not in their roots. So we only saw about a 10% survival of those willow stakes for that ramp outlet.
Okay, Jess, stay on, because next one I think is going to be you too. Would a grade difference of 0.95 feet at those step pools constitute a fish barrier? But I think the 0.95 feet was actually your pool depth though, right? Not your step difference.
Correct. The step difference was only 6 inches. And so coho and sockeye of that system have no problem passing. And when I was actually out there the other day, I was observing an adult salmon make his way on up with no issue. Okay.
For within culvert crossings, how critical is hyporheic exchange? And wondering about improvements using box culverts.
Yeah, I've been thinking about that a lot, actually. We tend to use box culverts a lot because they're easier to install and a little bit less expensive, and provide basically a protection for scour. You don't have to worry about the putting scouring out. So yeah, we're definitely losing that hyporheic exchange there. What I've been thinking about is you can actually get plate culverts with holes in them. And I think that might help improve that function. But, if you can do an open bottom culvert, that is the best scenario.
Yeah. All right. How was placement of the large boulders, the rock bands, the stream barbs, that sort of thing, achieved by the contractor in the prefabricated culverts? Kind of a follow-up to that, if you know, how heavy was the largest boulder, and do you know how the project's held up in recent storms?
Good question. Yeah, I have some pictures of some great equipment that they use to place this stuff. I've seen them up to 12-inch rock, basically place them by hand with wheelbarrows, but that's pretty rare. Usually they use there's a kind of a walk behind skid steer that is only like 4.5 feet of clearance. So you can get in a culvert with that, or a regular skid steer is about 6.5, 7 feet. So if you can keep your culvert dimensions 7 feet or greater, they use the skid steer to do that. I should have put some pictures in of that. It's always interesting. But then as like placing them, you know, the structures is they just work their way back out of the culvert. So they'll start in one end and start placing material. And so if there's anything that's messed up with the channel placement, then it all has to be redone by hand. So it's important to get it right as they go along.
Okay, we still have more questions. They just keep on piling up. So I don't think I'm really making much progress on this, but that's great. We've got still 9 minutes. We will potentially run out of time to get to all these. How would you wash in if you wanted finer sediments in the entire width of the culvert, not just in the middle? Won't this just wash out when connection occurs?
Yeah, we typically do wash them into the entire width of the culvert. So, I mean, it's just a matter of kind of going along with that high pressure hose and doing that. And if you take a look at that video, I think that'll make that a little clearer, maybe.
All right. Do you use an economic financial benefit calculator? And if so, can you share that?
No, I have tried to create an economic financial benefit calculator, and I decided I'm not an economist. So I've relied on looking at studies that others have done, but I can sure share that study that I quoted there. We'll share the PDF with folks, and I can make sure that our sources are there.
Yeah, and this kind of addresses the next question on there. We will be putting the PDF on our website, and eventually this recording will also go up on our YouTube channel. So both will be available so that everyone will have the QR codes in multiple formats. All right, I'm curious whether Alaska performs stream mitigation for impacts such as culverts, and if so, would a bottomless culvert with a stream built inside the culvert require less or no mitigation than a box culvert or pipe? So I guess just take the first part of that. You perform stream mitigation for impacts such as
well, so our usually if we're having a new culvert isn't being installed, we just have them or, you know, like Fish and Game will have them install it to meet the new standards, which pretty much require substrate in the culvert. Yeah, so I don't think that we're doing stream mitigation specifically for culverts, but so can sometimes be replaced as a mitigation banking, you know, tool, whatever. It's not really my area of expertise, but I have seen that, you know, where they've and absolutely, you know, when we see a culvert come in that's proposed for a mitigation banking, we would like to see as much stream function in it as possible. Thankful with the bottomless culvert if possible.
Yeah. Okay. We won't push you any further on mitigation questions then.
Yeah, thanks.
All right. What is the approximate order of magnitude, or what is the approximate or order of magnitude capital cost for small stream crossings under a 2-lane road?
Can you say that again? Order of magnitude of.
Do you have like an order of magnitude number in mind, or a approximate cost for a small stream crossing, which would be under a 2-lane road?
Right. Okay. Yeah. Well, prices are going up, and Alaska is a very expensive place to construct. But I'll give you on the road system in Alaska, we're basically seeing about $300,000 per crossing on sort of smaller 2-lane roads, and culvert widths about less than 20 feet.
There's tons of kudos in the chat for you guys. So scrolling through that, getting to the next question. How are you prioritizing which structure to replace next? Is this based on ecological needs or more based on infrastructure needs? And what's your primary funding source for the projects?
So we work in the National Fish Passage Program, which is a Fish and Wildlife Service program, and provides some funding for culverts. We also have a lot of partners that we work with, NRCS, NOAA Restoration Center, US Forest Service, BLM, the Alaska Department of Transportation, Federal Highways, the list goes on. So lots of federal funding available for culvert replacements, and we usually are combining multiple funding sources to do that. And what was the second part of that question? Sorry.
I think the second part, is it based on ecological needs or more based on
Right,
infrastructure?
prioritization.
Mhm.
Right, that's a sticky question. So yeah, it's hard to prioritize across the entire state of Alaska. Different watersheds have different, different stream links, might be more valuable in one watershed than in another, more productive. So, to say that, oh, this culvert's the best culvert and because it has the highest stream length may not necessarily be the case. So we kind of look at a prioritization per watershed, first of all. And we generally work with our partners in those different watersheds to, determine what might be a high priority. We're definitely looking at number of species present. We are looking at miles upstream, and cost and feasibility and funding sources available. And the state, Alaska Department of Fish and Game has done some prioritizations for different watersheds. We've done a prioritization for a watershed. So it's kind of, on a watershed by watershed basis.
Great. All right, there are several more questions, but I'm going to make this one the last one. It's just the next in line. How have you integrated scour countermeasures along the abutments for 3-sided culverts, e.g. integrated with stream bed design or separate lower layers?
We generally integrate those with the stream bed design. So we will continue like sort of the larger rock in the culvert, outside the culvert into the channel area. Sometimes we use sill plates or blanking on the name, but mostly we're relying on the stream bed design and the resistance of the rock that we put in there to protect the bottom of the culvert, both in open bottom culverts and in those with an out or that have an invert in them, because we don't want that invert to be exposed in either. That's the goal here. And I guess the other thing is we definitely use large rock along the footers. And that large rock, hopefully we get filled with a well-graded substrate, as Jess mentioned there.
This is great. Like I said, there's a few more questions in chat. Heather and Jess, do you mind dropping, you don't have to, but if people have more questions, could they get in touch with you? Would you mind sharing your emails in the chat?
Sure.
For people to get in touch, and for those of you who didn't have your questions answered, I consider sending it to them in an email. Thank you everyone for attending. This has been a great conversation, and thank you so much to Heather and Jess for putting this presentation together and taking time out of your busy fieldwork days to talk with us this morning.
Thanks for having us.
Yeah. Thanks, everyone. Thanks, Kathy.
Right. Thank you. I'm going to leave this on going for a little bit so that people can be sure to grab those emails that are dropped in there, but otherwise we will catch you all at our next presentation.